In this video, we will review all of the types of hypothesis testing that we've covered. We've covered one sample mean with the t-test, one sample proportion, two sample independent means, two sample dependent means, two sample independent proportions, and the chi-squared goodness of fit test. Here's our summary of 3 ways to perform hypothesis testing. In the classical approach, we need 2 pieces of information. We need a test statistic and we need a critical value. The critical value tells you the area of the shaded region, where that value starts. So for a two-tailed test, your critical values, you have part on the left and part on the right. And if your test statistic falls in either of these 2 regions, then we reject the null hypothesis. If we have a left-tailed test, alpha, our significance level, is only on the left-hand side, and our critical value would be here. If our test statistic is smaller than this critical value, then we will reject. In our right-tailed test, alpha is on the right-hand side, and our critical value is here. And if our test statistic is greater than our critical value, then we will reject. If we're doing hypothesis testing with the p-value approach, the only thing we need to remember is that if the p-value is less than alpha, our significance level, then we reject. If we're performing a confidence interval on a one-sample, two-tailed test, and once again, this is a two-tailed test, alpha is split over the 2 sides, then we reject the null hypothesis if our parameter, either the mean or the proportion, is not inside of our interval. If we're doing the confidence interval approach for a 2-sample, we reject the null hypothesis if 0 is not within our interval. So here's our hypothesis testing overview for the 3 types of hypothesis testing that we have been performed. Your critical value for all means, the function that you use in your calculator to find it is inverse t. When you're dealing with proportions, in order to find your critical value, you use inverse norm. And for chi-squared goodness of fit test, to find your critical value, use inverse chi. And this is a special program. It would be under program in your calculator if you haven't. If you have a one-sample mean problem, in order to find your p-value and your test statistic, use the t-test. If you have 2 samples with independent means, then you use 2-sample t-test. If you have a 2-sample dependent mean, you would put your data in L1 and L2, and based upon how your problem is worded in L3, you'll have to find the difference, and then you'll use t-test on the difference. For one sample proportion, you use 1 prob z test. 2 sample proportion, you use 2 prob z test. Chi-squared goodness of fit, you use chi-squared GOF test. If you don't have this in your calculator, you may have a program for this as well. If we're calculating confidence interval, for a 1 sample mean, we use 2 in t interval. And this is only if we have 2-tailed tests. If you're working with 2 sample independent means to find your confidence interval, you use 2 samp t int. If you have a 2 sample dependent mean, we use t interval on L3. So just like 1 sample mean, we're using t interval. If you have 1 sample proportion, we use 1 prob z int only if it's a 2-tailed test. If it's a 2 sample proportion and we want the confidence interval, we use 2 prob z int. And what you should notice is confidence interval, they all have interval or int in the title. If you're doing hypothesis testing for the p-value approach, they all have test in the name. Our null hypothesis is listed for each of our different tests. If it's a 1 sample mean, your null hypothesis is always that it's equal to a number that was given in the past. 2 sample independent means, the mean of sample 1 is equal to the mean of sample 2. For 2 sample dependent means, the mean of the difference is equal to 0. For proportions, the population proportion is equal to a certain number. And 2 sample proportions, the proportions of the two samples are equal to one another. Chi-squared goodness of fit, the null hypothesis is always that the random variable follows a given distribution. Here we have our alternative hypothesis. If you replace the equal signs from the null, it can be any of these tests. Not equal to means it's a two-tailed test. Less than, less sign means that's a left-tailed test. Greater than is a right-tailed test. For chi-squared goodness of fit, our alternative hypothesis is that the random variable does not follow the given distribution. So when we are interpreting our results, if we decide to reject the null hypothesis, then we can state our conclusion in any of these three ways. If we fail to reject our null hypothesis, we can state our conclusion in any of these ways. So where you can find all of these features in your calculator, if you press Stat and move over twice to Test, you will find all of the tests and all of the confidence intervals that you need. If you're defining the critical values, you use seconds and vars, and that will take you to distributions. And here you would have inverse norm, here you would have inverse t. In order to find the critical value for the chi-square test, you have to go into program. So tips for how to approach any of these hypothesis test problems. Make sure that you read the problem slowly. Identify the parameter in the problem. Is this a mean problem or is this a proportion problem? Proportions have percentages, or they ask a question in such a way that it is a binomial experiment. So you ask a question where the only answers are agree or disagree, pass or fail, right or wrong. There are only two mutually exclusive options for proportions. Identify whether you have one sample or two. If you have a two-sample mean problem, identify whether it's independent. The samples have nothing to do with one another. There's no relationship between the people in the first sample and the second sample, or whether they're dependent. Your two samples come from a matched pair. Husband and a wife, twin A, twin B, left side of the face, right side of the face. There's some way that you're able to match up individuals to each other in a dependent sample. Then perform your corresponding analysis. So here's our first problem. And you can always pause this video so that you can take your time to read it and see if you can perform the test. So here we want to know, do we have enough evidence to say that LA doctors work significantly less than the rest of California? So our null hypothesis here is that our mean is equal to 60. Your null hypothesis is always a given statement from the past or history that we assume to be true. So if the California average is 60 hours a week, that's the null hypothesis. That's the initial statement we're going with. Our alternative hypothesis, does the given evidence state that LA doctors work significantly less? So this is a left-tailed test, and the numbers are always the same, 60 and 60. So if we're doing the p-value approach, we have one sample mean. We're going to use the t-test, and mu sub 0 always comes from the null hypothesis. X bar is our sample mean, so from a random sample of 49 doctors, in our sample, they worked 53.1 hours with a standard deviation of 7.2. We select left-tailed test, and here are our results. So here is our p-value, and make sure you pay attention to that whole number. So E is scientific notation, which means this number times 10 to the negative 8th power. So since our p-value, which is basically 0.000, round to 3 decimal places, since that's less than alpha, we reject null hypothesis. If we did this using the classical approach, we find our critical value using inverse t. We find our test statistic using our previous test. Here's our test statistic on that top line, negative 6.71. And we compare our results. So here is our critical value at negative 1.68. If we plot our test statistic on this graph, we would see that it's in this shaded region. It's in the unusual area. So since it falls within the critical region, we reject the null hypothesis. Another way you can say it is we reject the null hypothesis because the test statistic is less than the critical value. So we're doing this two different ways, but our results should always be the same. Here's our next problem. Pause the video if you need time to read it. This is a chi-squared distribution. We want to know if our sample matches the given distribution according to Snoop Incorporated. For chi-squared goodness of fit test, the null hypothesis is always that our random variable follows the distribution. So what we need to do is to find the expected values. Here are observed what we see from our particular sample, and what we have are the percentages for the expected. So the way we find expected values, we take our sample size, 519, and multiply it by each probability. So in L1, we always put our observed. In L2, we always put our expected, and these are the values that we get from multiplying our percentages by our sample size. We go to our chi-squared GOF test. Observed is in L1, expected is in L2. Your degrees of freedom is your number of categories minus 1. So we have 6 separate categories based on ages. We subtract 1, so we have 5 degrees of freedom. And here are our results. Top line is our critical value. Top line is our test statistic. P is our p-value, and since our p-value is less than alpha, our significance level, we reject the null hypothesis. There is statistically significant evidence to say that the samples are different. If we do the critical value approach, we need a program inverse chi. You may or may not have that. We enter the degrees of freedom there. Chi-squared distributions are always right-tailed tests. So we enter the area to the right, which is alpha, 0.05, and we find that our critical value is 11.07. So when we plot our test statistic, the previous point that we had, 15.65 is our test statistic. Once we plot that, since it's in the shaded region, it's in the critical region, we reject the null hypothesis. Here we have 2 training programs. So since we have 2 training programs and we're looking at means, this is a 2-sample mean, and this is an independent problem because the dogs in program A have nothing to do with the dogs in program B. There's no ties between the dogs individually. So p-value approach, we want 2 sample t-tests. We enter in all the results for the first sample. Enter in all our results for the second sample. This is a left-tail test because we want to know, was the training for program A significantly less than program B? You always leave pooled on no. And here are our results. This is our test statistic. Right below it is our p-value. Since our p-value is less than alpha, we reject the null hypothesis. There's enough evidence to say the length of program A is shorter. If we do this with the classical approach, we find our critical value using inverse t. Inverse t takes our area to the left, and since this is a left-tailed test, the area to the left is alpha 0.01. When you have 2 samples, the way you find your degrees of freedom is you take your 2 sample sizes, and whichever one is smaller, you subtract 1 from it. So our sample size here is 40. So our critical value is negative 2.423. When we found our test statistic from the previous screen, our test statistic was negative 2.7. So when we plot that, since it falls within the critical region, the shaded area, we reject the null hypothesis. There is sufficient evidence to say that the mean length of time for program 1 is smaller than the mean length of time for program 2. If we do this using the confidence interval approach, we use 2 samp t int. You don't have to change any of these values, they stay the same. But what you do need to pay attention to is your C level. This is your confidence level. If you take the C level plus alpha, it should equal 1, meaning 100%. So alpha is 0.0901, so our C level is 0.99. Here is our confidence interval. If we were to interpret this, we would say that we are 99% confident that the population proportion of the difference between mu sub 1 and mu sub 2, those means, is between a negative 3.745 and a negative 0.0552. So since this interval does not contain 0, we reject the null hypothesis. Here, we have a right tail test. And the wording of the problem, you had to pay attention to this one. Initially, you would think that since it's dropped, it would be less than, but you have to read the problem. So in 1975, this was our first sample. In 1991, here's our second sample. So if over time, the proportion of U.S. adults who strongly agree with the statement has dropped, that means that in 1975, this number is larger than the value we received in 1991. So that's why it's a right tail test. So p-value approach, we use 2-prop-z test. Enter in our first sample and our second sample. Right tail test. Here is our p-value. Remember, E is scientific notation. So this is 7.21 times 10 to the negative 9th power, which is essentially 0. So since our p-value is less than alpha, we reject the null hypothesis. There's sufficient evidence to say that the proportion of adults in 1975 who believe people should take care of themselves is greater than that in 1991. If we do the classical approach, we find our critical value using inverse norm, because this is a proportion problem, and proportion problems always use inverse norm. Inverse norm takes area to the left. So since this is a right tail test, that means 5% of our data is on the right, and inverse norm takes area to the left, so everything that's on the left would be 1 minus 0.05, so 0.95. Standard normal distribution, mean is 0, standard deviation is 1. So our critical value is 1.64. And our test statistic that we got from our 2-prop-z test is 5.67. When we plot that point, it's far to the right. And since it's within our critical region, it's in the shaded area, then we reject our null hypothesis. If we're doing the confidence interval approach, we want 2-prop-z int. And once again, make sure you check for that C level. When you add the C level and alpha together, it should equal 1, standing for 100%. And here is our confidence interval. Since our confidence interval does not contain 0, then we reject the null hypothesis. Alternative hypothesis, we wanted to know, has the attitude changed? So, 1-prop-z test, there's only one proportion here. They only took one sample, and that one sample was in 1995. And P sub 0 comes from the null hypothesis. This is what we previously knew, what had already been accepted, and the information that we are basing everything off of. We enter X, the number of people with a certain characteristic. N is always our sample size. We have a 2-tailed test. Here is our test statistic. Here is our p-value. Since our p-value is not less than alpha, we fail to reject the null hypothesis. So there's insufficient evidence to say the attitude has changed. If we're doing the classical approach, we find our critical value using inverse norm, because this is a proportion problem. And with 2-tailed tests, when you're trying to find your critical value, you take alpha and you divide it by 2, because alpha is both of these tails together. So we just want this value. And we have our negative 1.64 as our negative critical value. But since this is a two-tailed test, you have another side as well. And since they're symmetric, we know the positive value, 1.64, is the other critical value. Our test statistic, 0.5, since it does not fall within those critical regions, we fail to reject the null hypothesis. For our confidence interval approach, we use 1 prop z int. Remember to check your C level. Your C level is the complement of alpha. So when we add these two together, it should give us 1, which represents 100% probability. So when you have one sample that you're using with confidence intervals, you're checking to make sure that that null hypothesis, if that value, is within that interval. So since 0.39, the null hypothesis, the statement that we're assuming to be true, since that is within our confidence interval, we fail to reject the null hypothesis. For our last problem, this is two sample dependent means, and they're dependent because the salesperson is the same. We can link these two values together because it's the same person. So our null hypothesis is that our mean difference is 0. Here we're testing whether the weekly sales is with the bonus is greater than the weekly sales without the bonus. So in L1 we put the weekly sales without the bonus. In L2 we put the weekly sales. In L1 we put the weekly sales with bonus. L2 put the weekly sales without bonus. We go to the very top, make sure our highlight is over L3. And we type L1 minus L2. This statement depends on the wording of the problem. Once we press enter, it automatically calculates the difference between these. We go to t-test and we actually have the data. Mu sub 0 comes from our null hypothesis. List 3 is where our differences are. We want to right tail test. Here's our test statistic. Here's our p-value. Since our p-value is less than alpha, we reject the null hypothesis. For classical approach, we need that test statistic. So to find our critical value, we use inverse t since this is a mean problem. Since this is a right tail test, our area to the right is 0.05, so the area to the left is everything else, 0.95. Our degrees of freedom, we take the number of salespeople minus 1. So our test statistic is 2.02. Our critical value is 2.02. Our test statistic is 2.88. And since this value is greater than our critical value, since it falls within that critical region, we reject the null hypothesis. If we're looking at this with the confidence interval approach, we go to data for under t interval. Our list is L3. C level, once again, is a complement for alpha. And here, two samples we're looking for is 0. So, since our confidence interval does not contain 0, then we reject the null hypothesis.